Electromagnetic induction is the physical process that powers global energy grids and dictates phenomena like magnetic braking. In this module, we will break down exactly how generators create that electrical power, how transformers modify its voltage for the grid, and how electric motors ultimately consume it. We will look at the exact mathematical models behind these devices. By the end of this video, you will be able to calculate the precise voltages and currents they operate on. Induction is a calculable, predictable force that dictates the engineering of the technology you use every single day. Let's start with the source. A generator's primary function is to convert mechanical work into electrical energy. The core mechanism involves rotating a wire coil inside a steady magnetic field. As it turns, the amount of magnetic flux passing through that loop constantly changes. According to Faraday's law, this continuous change in flux induces an electromotive force, or EMF, which drives an alternating current through the wire. We model the maximum voltage, or peak EMF, produced by this rotation using a specific equation. Epsilon peak equals NAB omega. Let's define these variables. N represents the number of turns in the wire coil, and A is the surface area of the coil, measured in square meters. B is the strength of the uniform magnetic field, measured in teslas. Finally, the Greek letter omega represents the angular velocity of the spin, in radians per second. The physical dimensions of the coil, combined with the sheer speed of its rotation, mathematically determine the maximum electrical push any generator can deliver. Once a generator creates power, we need to move it. Transformers are devices explicitly designed to step the voltage of alternating currents up or down. A transformer consists of an iron core wrapped with two sets of wire coils. Whether it acts as a step-up or step-down transformer depends entirely on the number of turns in the secondary coil compared to the primary coil. This relationship is defined by the core transformer equation. V sub s over V sub p equals N sub s over N sub p. The subscripts strictly track the source, which is the primary, P, and the load, which is the secondary, S. For an ideal transformer, we assume 100% efficiency. The power entering the primary coil must equal the power exiting the secondary coil. Remember, power equals current times voltage. Setting input power equal to output power gives V sub p times I sub p equals V sub s times I sub s. Because power is conserved, stepping up voltage means stepping down current by the exact ratio. By sacrificing current, transformers allow grid operators to boost voltage for efficient long-distance transmission, perfectly preserving the total energy flowing across the system. Let's apply this to a practical scenario, calculating the parameters for a video game console's wall plug. We know the primary coil inside the plug has 400 turns and draws a 120-volt input from the wall. The secondary coil has 30 turns. To compute the secondary voltage, we isolate V sub s. Multiply the 120-volt input by the ratio of 30 over 400 turns. This gives us exactly 9.00 volts output. Next, we find the primary current, given that the console itself draws 1.30 amps, which is our secondary current. Using power conservation, we isolate I sub p. We multiply the 9.00 volts by 1.30 amps, then divide by the 120-volt primary input. The plug draws only 0.0975 amps from the wall outlet. The calculated turn ratio allows a lethal 120-volt wall outlet to safely power delicate 9-volt electronics, balancing the current and voltage precisely. Now, let's look at the endpoint of that power, electric motors. Conceptually, an electric motor is a generator running in reverse. As a motor's coil spins inside its magnetic field, it induces its own EMF. By Lenz's law, this induced voltage actively opposes the driving supply voltage. We call this back EMF. To find the actual operating current, we use this formula. Current equals the supply voltage minus the back EMF divided by the motor's resistance. When you first turn a motor on, it isn't spinning yet. The back EMF is 0, causing a massive initial current. As the motor accelerates, the back EMF grows and the total current drops. A motor's own rotation creates an electrical defense mechanism. It actively prevents the motor from drawing destructive amounts of current once it reaches full speed. Let's calculate exactly how much that current drops. We have a motor connected to a 120-volt source with an internal resistance of 12.0 ohms. At its normal operating speed, the motor generates a back EMF of 100 volts. Our objective is to find the current draw under these running conditions. First, we calculate the numerator. We explicitly subtract the 100-volt back EMF from the 120-volt supply. This leaves a net effective voltage of just 20 volts. Next, we divide that 20 volts by the 12.0 ohms of resistance. The operating current is restricted to a very safe 1.67 amps. Explicitly subtracting the back EMF is mathematically essential to understanding why motors draw only a fraction of their startup power when running normally. Beyond wire coils, induction also affects solid objects. When a solid piece of metal moves through a magnetic field, the changing flux induces swirling electrical pathways inside the metal, known as eddy currents. This diagram shows the application of Lenz's law. These swirling currents create their own magnetic fields, and they are oriented specifically to oppose the motion that originally created them. This creates a frictionless braking effect known as magnetic damping. Because solid metal has internal electrical resistance, the kinetic energy doesn't just disappear. The eddy currents dissipate it by generating significant amounts of heat. Changing magnetic fields turn unwired, solid conductors into internal braking systems and highly efficient heat sources. These precise mechanics of induction are built into the architecture of modern technology. Computer hard drives read your stored data using tiny induced currents generated as the magnetic disk spins past the sensor. Induction cooktops use rapidly changing magnetic fields to generate eddy currents directly inside the metal of your pots, heating them purely through resistance. And security metal detectors locate buried objects by sensing the weak eddy currents induced in any metal passing through them. Let's review the core mechanics. 1. If the secondary coil has more turns than the primary, is the transformer step up or step down? 2. Why does an electric motor draw less current once it speeds up? And 3. What physical effect causes magnetic damping in a solid metal? Electromagnetic induction governs how we scale voltages, regulate motors, and generate heat across the entire electrical grid.